Hello everyone, my name is Anastasiia Poliienko, and today I would like to present you a topic on alternatively coupled Ising models that I was doing supervised by František Herman. So previous talk showed us that spintronics is quite interesting to study, meaning that if we will study systems with spins and look at how they behave, it can be a result in interesting things. So what we were looking at, the idea was to look at two chains of spins. So on the image, you can see the chain of spins, upper one and lower one. They all are coupled. And we are looking at those spins here at a classical representation. Still, we will see that it will show us a lot of interesting results. So, those two chains of spins are somehow interconnected as well, in a specific way. Here you can see the alternatively coupled system, and our goal was to compare those results with the ladder model that was studied by Marcel previous year. And what do we have different? We have one more additional coupling here. You can see that here we had, Marcel had couplings like this. We have the same couplings, but one coupling more, one type of coupling. So for the Hamiltonian, it will mean for us that we have the only one new term in it, in the energy function. And let's look at how the system will behave. So, throughout the work, we are using knowledge from statistical mechanics course, and those who had this course already know that we can use different ensembles there. And here, throughout the work, I use canonical one, where the studied thermodynamical potential is Helmholtz free energy. Note that it can be found by this equation, and note, it will be important later, that it is a real physical quantity. It consists of energy and Ts term, where T is temperature, S is entropy. It's thermodynamic definition, and also we will be using the statistical definition where to find the Helmholtz free energy, we will need to find the partition function, where partition function is the sum over all the microstates of such exponents. So, let's look at mean field theory results. We did the calculations and noted that in compared to the ladder model, where there are such couplings, we have factor of 2 near the J3 coupling. How can we explain it? We can explain it by the presence of the doubled amount of interacting spins, that each spin in the lower chain in the ladder model interacts with one in the upper, while in the alternatively coupled model, it interacts with 2. So, such results for mean field theory. And let's look if some other methods will provide us more differences with the ladder model. At first, we started to study the system at limit of zero temperature. Why? Because if we will look at Helmholtz free energy here in an intensive form, we will note that if temperature is 0, then this Ts term is 0 as well. So instead of studying the Helmholtz free energy, we can study energy of the system, which is obviously easier for us. And we started to look at different configurations that are provided here in the table and calculated energies for every configuration. And then, to find the configurational transitions, we were equating those energies. And what did we get? We get such plots. And the first plot, you can see the coupling of two ferromagnets, meaning J1 and J2 are equal to 1. I'm using here dimensionless constants. And we can see that for a positive J3, in this area, we have one phase transition. For negative J3, we have two phase transitions, and those are configurations that will be resulting in minimal energy for each pair of J3 and H. For two coupled for an antiferromagnet coupled with a ferromagnet, we have seen more configurations, and those are provided on the plot B. And as for me, the most interesting results were for the case C, the coupling of two antiferromagnets. And before, I was talking that we were equating energies for each configurations from the table. I will refer to them as two pure configurations. Here, in this light gray and light orange area, we can note that those are not kind of pure configurations. And this plot was investigated a bit later when we already knew how the system behaves while we were seeing the magnetization of the system. And if to compare the results with a ladder model, then we can see that first two plots are quite similar, while the third case of two coupled antiferromagnets is different. And let's try to explain why. We started to research the system at the thermodynamic limit. It's when the number of spins is going to infinity. So we wanted to change the structure of the Hamiltonian so that it's not the sum of infinite series, and we needed to change how we view the system, right? So we have come up with tiles. So instead of looking at the system as just some chain, we are splitting it to such tiles. And obviously the Hamiltonian will be rewritten at the sum of Hamiltonians of each tile. That can be defined in one way. Then we started to build up a transfer matrix. We chose some bases. The Hamiltonian is rewritten as sum of Hamiltonians of each tile, and it helped us to define the partition function, as I was referencing to as sum of Boltzmann weights. And individual elements of the transfer matrix would be such exponents. And on the next slide, I'm showing this transfer matrix when we realized that it is not symmetrical. You can note those elements that are not symmetrical. We understood that it can be a problem. Why? Because we are using this matrix to find eigenvalues, and after looking for eigenvalues, we look for the partition function. And we know that if the matrix is not symmetrical, then we are not guaranteed real eigenvalues. Still, we need to find some real physical quantity using this not real eigenvalues. So how did we solve this problem? We've understood that when we are solving the characteristical polynomial for such a matrix, and we have there a root of a complex eigenvalue, then this root will be paired with its complex conjugate. That if, let's say, lambda 1 and lambda 2 are real, and here two eigenvalues are complex, so if one of them is complex, then another one is complex as well, and it is paired with it. So we can rewrite their sum as a cosine function, which is real, and we have solved this problem that even though we can have complex eigenvalues, we still have a real partition function. And all of that we wanted to do in order to find the Helmholtz-free energy using this partition function. And if we derive it by H, then we can investigate the average magnetization of the whole system and of the subsystems separately. And here it is provided the plot for the magnetization of two coupled ferromagnets. As we expected from the limits of zero temperature, we see one configurational transition for positive J3 and two for negative 1. Next, we have looked at the case of coupled antiferromagnet and ferromagnet. Those are plots for the whole magnetization, for the average magnetization of the antiferromagnet and magnetization of the ferromagnet in such a system. And we have observed peaks on the plot B, same as were observed in the ladder model. And those peaks are explained by the temperature fluctuations. Next, we have looked at magnetization of two coupled antiferromagnets, and here I think where we got the most interesting and new results, because note that the system will be in the state of magnetization -1/3 here and 1/3 there. And it is happening for the negative J3, so for the antiferromagnetic coupling between the two chains. How can we explain it? And that's exactly those two areas, those light orange and light gray area in the case of limit of zero temperature. We understood that if we want to obtain the magnetization of, let's say, -1/3, average one, then we will need to combine some phases. And the whole two areas will result in a combination of those pure phases, while before we have only seen such a behavior on phase boundaries. And here we understood that we need to combine phases eta A, delta, and eta B. And later we understood that it can be redefined as the repeating of tripods, green ones and purple ones. And that's how are those light gray and light orange areas are looking. Next, let's look at some phase transition from configurational transition from such a configuration to some another one. We have seen that the magnetization of -1/3 needs to be transferred to the magnetization of 0. Let's talk about the whole system. And the interesting thing is that those spins will be behaving in a way that those tripods that were purple before will stay the same, while all the spins in green tripods will be flipped. And that's what will happen in the whole system. And it will be the best for the system, for this transition. So, to conclude, what did we have? In compared to the ladder model, we only had the factor of 2 in the mean field theory, and still other methods showed us more interesting results. We have dealt with a not symmetrical transfer matrix, which end up not to be a problem, and we have observed the rectangular structure as the case of two coupled ferromagnets, this area here. Also, the configurations in the peak that I was showing for a coupling of ferromagnet and antiferromagnet, we have seen more configurations there that are showing that peak, that are making that peak. And as for me, the most fascinating result was that we've understood that the whole two areas will consist of not pure phases, that they will consist of combination of those pure phases, eta A, delta, eta B, and we can redefine them as tripods. And still, remembering that this was a classical representation of spins, gives us, and still it gives us not trivial results, we can understand that if we look at the system in quantum model, it will be even more interesting. Thank you for your attention. That's all.